So good afternoon, everyone. Welcome back to this second session of the day. And this is again Andrea Ferretti from CNR Nano chairing. And we are now getting to the first hands-on session of this tutorial. Here is the program of the day. So after this morning lectures, now we'll have an hands-on led by Nicola Colonna from PSI and Iurii Timrov from EPFL, DFT in practice, from simple to advanced functionals, just set the stage. So LDA, GGA, meta-GGA, and hybrids. Then we'll have 15 minutes coffee break, then a lecture by Giovanni Pizzi, and a second hands-on by Antimo Marras and Junfeng Tiao. Okay, so let me leave the floor to Nicola and Iurii, please.
Thanks, Andrea, and good afternoon or morning, everybody. So this is Nicola Colonna, and I'm gonna run this hands-on session together with Dr. Iurii Timrov. So hope you can see my slides. So as you all know, the entire hands-on session will be run on the quantum mobile virtual machine, and you should have get information on how to get the material for the hands-on in one of our emails from yesterday. So if you haven't done yet, so please keep in mind that this is the repository, the Git repository where the material is hosted, and it's good if you start the virtual machine so that you are ready to run the tutorial and we don't lose too much time. Okay, so let me just go to the very beginning. So this is a first hands-on on DFT in practice. So it's from simple to advanced density functional. What do I mean with this? Essentially, we are gonna go through some basic or brief recap on Kohn-Sham density functional theory, essentially what are Kohn-Sham equations, how they are implemented in quantum espresso, and what are the typical approximation for the exchange and correlation energy functional. And then we'll do, I'll do myself a first very simple exercise on how to compute band structure of bulk silicon using the PBE functional, and how to compute the band gap again silicon using an hybrid functional scheme as the one you heard this morning by Professor Kronig. And then Iurii will take care of the other two exercises, and he'll show how to run meta-GGA function. Now, this is a kind of mixture between an hands-on and the lecture, because you heard about hybrid functional, but maybe it's good to iterate a bit more and to go more in detail, essentially on what is implemented in quantum espresso and how it is implemented. So I'll first give you a brief introduction, and then we'll go to the actual exercise. So let's start with the introduction. So this is a recap on Kohn-Sham density functional theory. So the idea behind Kohn-Sham DFT is essentially to establish a mapping between the system of interacting electrons that is in practice impossible to solve. This is a many-body problem. To map this system onto an easier one, or much easier one, that is a system of non-interacting fictitious particle, the Kohn-Sham particle, that moves in an effective potential. Now, this mapping is exact, and this means that you can get access to the total energy and the ground state density of your interacting system, simply solving a set of single particle Schrödinger equations that are the Kohn-Sham Schrödinger equation that essentially describes the electron that moves in this effective Kohn-Sham potential. Now, this is, from a computational point of view, very easy, much easier to solve the many-body Schrödinger equation, but you have to pay the price that you don't know how the mapping is performed. So you know that this mapping exists, but you don't know how to, in particular, approximate the, so you don't know the exact expression for the exchange and correlation energy function. And this is what typically we need to approximate, because essentially this enters also in the definition of the effective potential through this derivative. So we are lucky enough that people tackle this problem, and already since a couple of years after the introduction of the Colonna mapping, Colonna themselves proposed a very simple approximation that is based on the so-called local density approximation, where essentially the energy density of the homogeneous system in any point in space is approximated with that of an homogeneous electron gas that has a density that is equal to the local density of the real system. Now, in practice, this means that the LDA energy is expressed as an integral, where the only ingredient is the energy density of the homogeneous electron gas. And this can be computed once and for all with a very accurate method, in particular quantum Monte Carlo calculation. You store it, you fit with some analytic form, and then this means that anytime you get a density, you get a number for this object, and you can do this integral very efficiently. And this approximation is good in for many material in most approximation, but has some limitation. For this reason, people also try to improve it. And the very first big improvement was through the generalized gradient approximation, where essentially you include not only the information about the local density, but also the information about the gradient of the density. And this you have, while for LDA you have a unique way to compute this energy. Maybe the parameterization of the energy is different, but there's a unique LDA function. For the generalized gradient approximation, you have many, depending on the way you choose this enhancement factor FXC. And for this reason, you have many GGA approximation. Probably the most famous one is the PB approximation. You can do even better, include extra degrees of freedom, and this is what Iurii is gonna show you later on. For instance, the Laplacian of the density, or the density kinetic, and this is named meta GGA functional. And again, you have many of those. In particular, you'll see how to use the famous scan function. And finally, we will also discuss about hybrid function that essentially mix a fraction of Fock exchange with the local exchange, as Professor Kronig explained this morning. How this is implemented in practice? So I say Colonna equation are a kind of integral differential equation, and you have to solve in a computer. So in Quantum Espresso, this is solved introducing a basis set. And as a basis set in Quantum Espresso, we use plane wave. Now, this is one of the possible choices. There are many other choices. There are some advantages and disadvantages in using plane wave. One of those is that this is a basis set that is naturally compatible with the periodic boundary condition. But essentially, the idea is that we can expand all the quantity of interest, in particular the Colonna orbital, as a linear combination of plane waves. So here you have your plane wave, and you have some coefficient. Now, you have to remember that in any periodic boundary condition, what you simulate is really an infinite replica of your system. So this means that no matter what, your system is going to be periodic. And this means that you don't have all the possible plane wave, but you only retain the Fourier components that are compatible with the periodicity of the lattice. Now, this can be a supercell where you put inside your finite system, or really the primitive cell in a perfectly periodic crystal. Here I sketch an example for 2D, and this is what we call G vector. So all the G vector that enters in this expansion are those that form the so-called reciprocal lattice vector. And these are described as a linear combination of the so-called primitive lattice vector in reciprocal space. Here I call B1 and B2, that if you want in this plot are vector connecting these 2 points along y and these 2 points along x. Now, this is for 2D. In 3D, you have to imagine you have a cube and not just a square. But still, those are infinitely many. So you see n1 and n2 are integer numbers. So you have infinitely many G vectors. So you have to decide how many to choose. And what is typically done is that you take all the G vectors that have modulus lower than a given value, G max. And this is typically done in quantum espresso, setting a cutoff for the kinetic energy. Essentially, the kinetic energy cutoff is simply related to the modulus of this G max. And in quantum espresso, you specify this value, a cut wave function, that is an input parameter for a cut. And this really specifies the number of G vector you want to include in your calculation. Of course, this is a converging parameter. You need to increase it until you converge the property of interest, and we'll see how to do that. Now, you have to remember that actually in a perfectly periodic crystal, the Colonna states are not periodic within the primitive cell. You should remember from your quantum mechanical lecture or material science lecture that those are block state. So actually are written as a phase factor times a wave function that is periodic on the primitive cell. So all the discussion above apply to this object, but you still have this phase factor here that you have to take into account. And actually K is a quantum number for an electron in a system, is a quasi-momentum. And actually one can show that this belongs to the so-called first Brillouin zone of the material, that in these two-dimensional cases, this square here. And actually, all I said before applies. You still keep all the G vector that satisfy that are inside this sphere, but then you also need to accurately sample the first Brillouin zone. And this is what is done in quantum espresso with the card Keypoint that we are gonna use later on. Okay, and very briefly, last thing I want to touch is the use of pseudopotential. So essentially, the idea is that you replace the Coulombic potential with something that is smoother than that, essentially because you want to afford a plane wave calculation. So the idea is that typically wave function, especially for outer electron, displays this very rapidly oscillating behavior because they have to be orthogonal with the core electron. And this is something that is very hard to describe with plane wave. You would need a large number of plane wave to accurately reproduce this rapidly oscillating behavior. So the idea is that we can introduce a pseudopotential. Essentially, we froze the core electron close to the nuclei, and we can replace this rapidly oscillating behavior with something that is smoother. And the pseudopotential needs to be constructed in such a way to keep the shape of the wave function exactly identical to the all electron one outside a cutoff radius that describes my fictitious system of the nucleus plus the core electron. Now you have different recipe to do that. We're not gonna go into detail. You have not conserving pseudopotential or ultrasoft or projector augmented wave pseudopotential. But the important message is that you need to have such a pseudopotential if you want to run a quantum espresso calculation. And again, you are lucky enough that people already addressed this problem. This was a project led by Gianluca Prandini and Attimo Marrazzi in the group of Professor Marzari, and they came out with this very nice table where for each element in the periodic table, you have the best pseudopotential available, meaning the best that match an all-electron calculation. So on this web page, you can find this table. You can even download the entire set of pseudopotential, and this is something you store on your computer. Anytime you have to run a calculation, you point to this directory, and you use this validated set of pseudopotential. Again, this is not the only choice. You have other places where to find pseudopotential, the Quantum Espresso web page. And there are sometimes codes, like in particular Kubman, that actually do not support all the different kinds of pseudopotential. We are forced to work only with non-conserving pseudopotential. For this reason, we have also very nice library that only contain non-conserving pseudopotential. In particular, it has G15 or the so-called pseudo dojo. Okay, and this was just a brief recap. Now we are gonna see how to run a quantum espresso simulation in practice. So, and the first thing we are gonna see is how to compute the PBE band structure of bulk silicon. So essentially, what you have to expect from this tutorial, essentially at the end of this first exercise, you should be able to compute a plot like this. So this is the band structure of bulk silicon. And essentially, this is a fundamental property of a material, carries a lot of information, in particular, whether the system is a metal or an insulator. In this case, you know, silicon is a semiconductor system. It has an indirect band gap between the gamma point, and this is the top of the valence band, and the point that is somewhere between gamma and X, and this is the bottom of the conduction band. So the structure, silicon is an FCC, so it's a cubic material. Here what I show is the conventional cubic cell, but actually the primitive cell of the material, so the smallest cell you can imagine to reconstruct the perfectly periodic crystal, is represented by this bold line here, and is described entirely by these three primitive lattice vector, A1, A2, and A3, and they point toward the center of the face of this cube, and this is the reason why it's called face center cubic. And inside this primitive cell, you have two inequivalent silicon atoms, one sitting at 0, 0, 0, and one sitting at 1, 4, 1, 4, 1, 4, so along the diagonal of the cube. So the crystal structure is something that you have to provide as an input to your, at least as a starting point for a quantum espresso simulation. And then we have an alternative description of the system in residual space. So this is, if you want, a primitive cell in a residual space. And this is a BCC lattice, is the reciprocal lattice of the FCC. And here, just to show you that you have a label like gamma, L, K, W, UX that you see along this path in the Brillouin zone, and they specify high symmetry point in the Brillouin zone. Gamma is the center of the Brillouin zone. X is something that lies in the middle of this square here. How do we put this information about the structure in quantum espresso? Well, this is how the input looks like. The first thing you have to do is to solve actually the Colonna equation. So you have to tell quantum espresso that what you want to do is a self-consistent field calculation. So you want to solve the Colonna equation until you get to the ground state energy and you find the ground state density of the system. And here you specify other quantities we'll see in detail in a couple of slides. And here it's where you specify the structure of the system. This is what I was describing in the previous slide. So you have a simple way to tell quantum espresso which Bravais lattice you are dealing with. So this is I Brav equal to 2 means we want to describe an FCC lattice. Of course, there are many different Bravais lattice. If you want to know what exact number you have to put in for your system, you have all this information in the Quantum Espresso web page and in the documentation for the PW. So in this case, in FCC, so it's I Brav equal to 2. And then, since this is a cubic system, the only things that specify the crystal is really the lattice parameter of this cube, and this is called cell DM1. If you have more complex system, you would need to specify other parameter. In this case, we use the experimental lattice value that is 10.262 Bohr. And then we have to tell to the code that actually, in this case, in this way, we specify the cell of the system. We need to specify how many atoms you have in the unit cell. And as I was saying, you have 2 silicon atoms. So you say we have 2 atoms. And actually, you specify that they are all of the same kind. So here we have all silicon. So the type of atom is always the same, and it's only 1. For instance, gallium arsenide has a very similar structure, but now you have, again, 2 atoms per cell, but they are different. So in that case, you would specify n type equal to 2. And this is the parameter I was mentioning before, one of the most important one for converging your calculation, the cutoff on the wave function. And we need to decide what value to put here. So this is something you always have to do in before running a meaningful calculation. Here you have some extra information, the convergence threshold for the SCF. So this essentially tells the code when to stop while doing this self-consistent calculation. So if the total energy between the step n and the previous step is lower than 10 to the minus 8 Rydberg, this means that we have achieved the convergence and we stop the minimization. And here it's where you specify the name of the pseudopotential. So this is actually the name of the file where the pseudopotential is stored. This is actually only the name, but in the name list control, you need to specify also where physically in your computer this file is, and this is the path to the folder containing the pseudopotential. Finally, you need to specify the position of the two non-equivalent silicon atoms in the cell. And as I was mentioning, one silicon sits at the origin and the other along the diagonal at 1/4, 1/4, 1/4. And this is what you specify here. And you use as a unit to specify this position the lattice parameter. So a lat is this object here, and then of course the silicon sitting at the origin is 0, 0, 0, and the other one is simply 1/4, 1/4, 1/4. And last, very other important converging parameter is the sampling of the Brillouin zone. As I was discussing, you need to find the proper value to put here. Essentially, this would give you a regular mesh on how to sample the Brillouin zone of the system. So you need to specify how many points you want to have in this regular grid to sample the Brillouin zone. Okay. Now, since well, we have very short time and we want to go very quickly to hybrid functional calculation, I did the convergent test for you, but I just want to show you how to do this in practice. Essentially, the first thing you want to converge is the cutoff energy. So typically, what you would do is that you choose a Keypoint mesh. So for instance, I choose 12 by 12 by 12, and then you repeat several calculations, changing the value of the cutoff in this input file. So here you put 12, 12, 12, and then you change this value here, and you do several calculations. Here I did for 20 Rydberg, 30 Rydberg, 40, 50, 60, and 80. And you see that here I plot the total energy of the system, and you see that at a certain point you reach a convergence, and you can safely choose 40 Rydberg as a converged value. Now, since we are interested in the band structure, I also monitor how the bandgap, the direct bandgap at gamma evolve as a function of the cutoff. And again, you see that already at 40 Rydberg you are converged. And the same is true for the indirect bandgap. So this means that 40 Rydberg is a good value, a converged value for the expansion in plane wave. And this is what we are going to use. Then the other parameter you would like to converge is the sampling of the Brillouin zone, and this is controlled by Keypoints. And again, I did it for you. In this case, now I know how to choose my cutoff, and I set it to 40, and I did several different calculations, increasing the sampling of the Brillouin zone. I first use a regular grid with 2, 2, 2 Keypoint, then 3, 3, 3, 4, 4, 4, and so on and so forth, up to 12, 12, 12. And you see, and again, the total energy converts very smoothly, and probably already at 8 by 8 by 8 we are converged, and the same is true for the gap. So this is what you typically have to do before running the final calculation. This is called convergent test. So something that you always need to remember to do to have a proper convergent calculation. Okay, so now that we can really go to the actual end zone and see how to really set up all these calculations, how to really run the calculation. So let me go to the quantum mobile but maybe we can take 5 minutes to check whether there are urgent questions to answer on Slack. Seems no, so I'll go to the the virtual machine. So I already have it running. So okay, this is the terminal. So but if you already start your virtual machine, you should see something like this. This is the desktop of your virtual machine. So the first thing you have to do is to open a terminal. This is something that you already did. And now you see something like that. If you list the content of the folder, you see all this folder. If you already clone the repository, you should also see this folder here, Abar-Kubman 2022. If you didn't clone it yet, so please do it. And oops, apologies. And this is where to I mean the command that you have to run in the terminal. So maybe I can put it in the chat. Everyone. Okay. So I put in the Zoom chat the command you have to run, but hopefully you sorry, you already did that. So let's go back to the virtual machine. Now I have my Abar-Kubman folder. I go into it. I list the content, and you see, first of all, a README file, and this is kind of a very general introduction on this tutorial. This is also what you see in the on the GitHub repository. It's explained essentially what is a quantum mobile, what this tutorial is about, and there is a kind of very general explanation of the exercise. So in day one, we are going to use hybrid function and method GGA to compute the band gap of bulk silicon and magnetic moment of bulk iron. So let's start. Let's go to day one. And now you see different exercise. And let's start with exercise 0, which is what I was showing in the slide. So in this folder, you see different file. And you see in particular silicon.scf.in. So this is the input to run the SCF calculation. This is what I discussed until now. So let's open it again. You can open with this command. And you see again, you see what I already discussed. What we are going to do is an SCF calculation. This is something tells the code where to store temporary files that are produced during the calculation. So this is the directory where to find the pseudopotential. So this in this directory we need to have the actual pseudopotential we are going to use, in particular this one. This is the prefix we decide to give to the calculation. It's probably self-explanatory. It's silicon. And here again, I just report the information about the structure that I described with the slides. And here now we know how to set these parameters. So I already said it for you. Its 40 readback should be it's enough to have a meaningful calculation. And again, this is the pseudopotential file. And now we use a Keypoint mesh of 12 by 12 by 12. And this is the position of the silicon atom. Okay, now we are ready to go. We check our input file. Everything looks in place. How do we run this in practice? Well, if you open the README or simply, let's do like this, we list the content of this README file. There is some very basic instruction on how to run the code. So pw.txt is the main drive of Quantum Espresso. Essentially, it's the code that performs, among other tasks, the self-consistent calculation. So we are gonna run like this, pw.txt, and then we give the input file. we saw is silicon .scf.in, and then we ask to redirect the output in this file. So typically we call .in input file and .out output file. Now we are ready to go. Okay, and you see the calculation start. So let me go, while it's running, I can explain to you what is happening. Well, this is just an introductory. That's how to cite the code. Here there are some information on the parallelization. Now we are running only on one process. Okay, then we have something more interesting, in particular the summary of the input structure. Here you see again that the Brave lattice is 2, meaning an FCC. Okay, this is the lattice parameter, the unit cell volume. This is just a recap of the input parameter. Again, how you specify the cell, you just need the lattice parameter. Here we see some information on the exchange and correlation. So this is something we didn't put in input. It's something that the code understands simply looking at the pseudopotential. So the pseudopotential we are using is a pseudopotential generated using the PBE function, and this is for consistency you need to use the same pseudopotential. If possible. We'll see that this is not always possible for meta DGA or hybrid, but for standard DFT this is always the case. So you automatically use this. The function that you're going to use is the same as the one you use to generate the pseudopotential. You have information also about the reciprocal lattice vector, some check on the pseudopotential. Then the code performs some checks for you, tested if you have symmetry operation, so symmetry that leaves the crystal unchanged, and is a summary found 48 symmetry operation, and those are used to speed up the calculation and reduce the number of inequivalent K-point in the sampling. Indeed, if you remember, we specify a regular grid of 12 by 12 by 12, but at the end, thanks to this symmetry operation, only 72 inequivalent K-points need to be computed, and this is where the code lists those. Now let's go really to the SCF loop. Here you see different iteration, meaning that the self-consistent procedure is going on, and after, in this case, very few iterations, 6 iterations, you see something like end of self-consistent calculation, meaning that we reach the threshold we specify in input, and the calculation is converged, and then it starts a report of the single particle eigenvalue or Cone-Sham eigenvalue at all the different K-points you have in your simulation. So this gamma and then many other, those are all the 72 inequivalent K-points. And at the end, for convenience, it's also reported the highest occupied, the lowest unoccupied energy level that gives you the band gap of silicon, and the total energy, which is the ground state energy for this system. And that's it. The calculation is very fast. It took 30 seconds in this virtual machine. And that's all. This is if we now list in the output, sorry, the directory, we see the output file where you can eventually open it, but you see the same content I went through. But you also see this output directory where you store all the temporary file or files that are needed for a restart, as we will need for the next step, which is a band structure calculation. So let me go back to the slide. This is what we actually see and we run just now. Now what we want to do is to produce this band structure. So now that we have computed the ground state density, so we have defined what is the ground state density of the system, we can restart the calculation. In this case, we don't do any more a self-consistent calculation, we do a bands calculation, meaning that we want to diagonalize the connection Hamiltonian on a selected number of Keypoints. And this is how we specify them. So the Keypoints now is given in crystal units, so in the unit of the reciprocal lattice vector, and underscore B stands in a band format. That means you need to specify the number of high symmetry points you want to use, so 5. So you'd see 1, 2, 3, 4, 5 high symmetry points are listed here. And then you specify, so this is the coordinate, the first 3 numbers are the coordinate of the high symmetry point, in particular 1/2, 1/2, 1/2 is what correspond to the L point in the Brillouin zone. And then this 4th integer number specify how many points you want to have between this high symmetry point and the next one. So we want to draw a path that goes from L to gamma, and we ask Quantum Express to generate 20 intermediate points between this line. And the same, then we go from gamma to X, and we put other 20 points, and so on and so forth. And the input for this file is band.in. And here again, now you see, we specify that the calculation is band. All these parameters needs to be the same as the one you use for SCF, because essentially now the code search for the restarting file in this directory. Again, you need to provide where the pseudo are. You need to use the same prefix used for the SCF. And again, those are all the same quantity. Now we specify something different. Now we want to compute a few more bands. So we want to have access not just to the 4 bands band, we want to see also some empty bands. So we specify this with this input variable and bands, and we set it to 12. So we are going to see 4 occupied band plus 8 empty bands. And again, this is the path we want to compute the band structure on. Okay, let's go to the terminal. Again, the executable file is again pw.txt, but you can again list the content of the readme.txt, and it tells you have to run this command. And now it's doing the simulation. So if you remember, we have 20 points between 5 high symmetry points. So this amounts to 81 independent K-point calculation, and the code is running each of those. So at each K-point, the Hamiltonian is diagonalized to get the eigenvalue at that point. And this is something that again is very fast for this simple system. Takes less than 1 minute on this machine, and that's all. Now, if I go a bit up, you see that now we have for each K point, given 1, we have 1, 2, 3, 4 occupied band plus 8 empty that we ask for. Now, all this information are again stored in this output directory. In order to extract it and to have a file that is easy to plot, we use a post-processing tool of Quantum Express that it called bands.txt, and the input file is bands.in. Essentially, you tell simply the code where to find for the output file. Again, you need to specify the prefix and the directory, and then you just specify where you want to store this data file that is easy to plot. And it's again very easy. So very fast. You list the content of your folder, and now you see that you have generated this file that you can open and inspect it, and you see a list of a 2-column file. This is the key path, and this is the eigenvalue for the first bands, and then you see the second bands, and so on and so forth. And to plot this, I prepare for you a file GNU-plot. So you use GNU-plot to plot it, GNU-plot plot bands.new. And you generate it to file with the result. You can open it with the display. And this is the outcome of the calculation. So you see we were able to generate this plot I show you at the beginning. So let me go back to the presentation and discuss a bit. So this is now the result of your calculation. This is the band structure of silicon with PB. If I zoom in, we can now inspect some of the basic property I was discussing. So the indirect band gap, so the minimum energy you need to promote an electron from the valence to the conduction, and this is 0.57 electron volt. The direct band gap is 2.56 electron volt. But if you compare with experiment, this is not very good. In particular, the indirect band gap is 1.17 electron volt, so PB is greatly underestimated, and the same is true for the direct band gap. There is also almost 1 eV electron volt difference. And this is the well-known problem of band gap with DFT with band gap. I mean, it's a very fundamental problem, but this, in a sense, prevent you to use blindly simple local singular function to predict such kind of property. So one way to go beyond this is to switch to hybrid, as Professor Kronig was showing before, and let's see how to do this with quantum espresso. Now, before going to detail, a few words about hybrids. As I said at the beginning, essentially the idea is to mix a fraction of exact exchange from R3-Fock with some semi-local exchange. So the idea is very old, dates back to 1993, when Becke first introduced this idea. And the idea how to mix, so the way how to mix the Fock exchange with the semi-local GGA exchange and correlation in this very first paper was simply to fit some thermochemical data on some more experiment or accurate quantum chemistry, and to find the best parameter A0, AX, and AC that completely specified your hybrid function. This was probably the very first very successful hybrid function. It's the famous B3-LEAP, and this was probably when chemists really start using density functional theory, because they were really able to have accurate result with the density function calculation with this scheme. Few years later, or actually a couple of years later, Beck himself simplified the approach and went back to what is called probably the simplest hybrid scheme ever, where essentially you mix some local exchange with the Fock exchange, and you leave the entire correlation from DFT, and the mixing parameter is called A0, so you have one parameter, and in particular, if you choose it equal to 1/4, you have the well-known and famous PB0 approximation. So in this scheme, you only need to set one extra parameter. And again, here is just some information more on what, or just a brief summary of what Professor Kronig showed this morning, that the next step in this very promising and active field of hybrid function was to introduce this range separated hybrid function. Now you should be familiar with this. So you first rewrite the Coulomb interaction, and you divide in a long range part and a short range part, and you treat the long range with the at R3-Fock level, and you treat the short range at DFT level. And you need to you have an extra parameter, is the range separation parameter, and this was very well explained in the lecture this morning. But this is a very general and form, and you can recover what we already know. For instance, if you set B equal to 0, you go back to the conventional hybrids. In particular, then if you also set A equal to 1/4, you go back to PB0. So you have no range separation, and you are back to the PB0 function. Another very famous and very used hybrid function is the HSC function. It's a range separated function. In this case, the mu parameter again was fitted on thermochemistry on a set of experimental result. And in this case, A is equal to minus B equal to 1/4. Again, this is from PB0, but you have a range separation parameter. And now here it's where you want to enforce exact constraint. In particular, you want that for finite system, the asymptotic potential goes like 1/r, very far away from the system. Again, this was very well explained in the lecture by Professor Kronig. And then you need to have that A plus B needs to be equal to 1. But this is the correct behavior, asymptotic behavior for finite systems. So in a system in vacuum, if you have instead a perfectly periodic crystal, the asymptotic behavior is no more 1/r, but it's 1 divided by epsilon r, where epsilon is the macroscopic dielectric function of your system. So you have some exact condition to impose in such a way to choose in a reasonable way some of the parameters. Still, you have some free parameter like the range separation, and you can either fit on experimental data, or as Professor Kronig was showing, you can also impose or tune this parameter enforcing the ionization potential theory. Okay, how this is implemented in quantum express? Well, essentially, you need to evaluate an extra term in your energy, that is the Fock, R3-Fock energy, that in plane waves looks something like this. So this is a real space integral over R and R prime. You can also transform this to reciprocal space, and this is what is done in quantum espresso. And then if you look at this expression, you immediately see that you have an extra integral over the Brillouin zone and the sum over the G vector. And this again is expected. And then you have this auxiliary function that in itself contains an integral over the Brillouin zone. So now you immediately realize that this is way more expensive than a standard DFT, where in any case you just have one summation over the Brillouin zone. Now you have an extra summation. And also the other very difficulties in dealing with this object is that you see that for Q and G, Q plus G that goes to 0, you have a divergence. But actually, you can prove that this divergence is integrable. Still, you have something that is a very steep function that you need to integrate very well. So in principle, you will need a very large number of Q points to convert this integral. But for this, you have people develop some very smart scheme to facilitate this convergency. And what we are going to use is the so-called Gigi-Baldereschi scheme, and there are flags in the input file of Quantum Espresso that you need to set to enable this scheme, and those are the exact exchange divergent treatment and the X gamma extrapolation. Those are set in this way by default because they are very, very effective, but I'll show you just to give you a sense. And then again, you have also, in this case, a sum over G vector. And again, there is a separate cutoff for this sum. So it's controlled by E cut Fock. By default, this is equal to the cutoff on the density, but you can also play with it if you want to speed up your simulation. But again, it's a converging parameter, so you need to be careful. If you change it, you need to do convergent test and be sure that nothing is going to change. And the integral over the Brillouin zone, by default, you use the same number of K points you use for the standard PB SCF calculation, but you can also reduce them, and the relevant parameter are those three. So again, here now I show you in detail how the input file looks like, and in particular I just show the relevant flags, the relevant input file. I don't want to go through. I mean, all the rest is pretty much the same as for PB. Now, in this case, you need to tell the code essentially which function you want to use. Essentially, here we specify this with this input flag, and it's input DFT equal to PB0, but it can also be B3LEAP or HSC. Then you specify the number of Q points you want to use, and something that I didn't stress before is that this Q point needs to be commensurate in any case with the mesh of K point you use in this flag. So in this case, it's 12, 12 by 12, meaning that here this can be 12, 12, 12, or 6, 6, 6, 444, 333, or any combination. It needs to be a divisor of this number. And then we instruct the code to use the Cauchy-Baldereschi scheme and to use an extrapolation for gamma, where we have this singularity. And then there are the Cutoff is a converging parameter that you can modify if you want to speed up the calculation. And there are also two extra parameters that you can use if you want to change the fraction of exact exchange. So we know in PB0 we are going to use 1/4 or 0.25, but if you want to do a different scheme and you want to change this 0.25 and you want to go to 0.3, you can specify it in here, and this is going to modify your hybrid function. And the same is true for the scaling parameter, so the range separation parameter. Okay, and again, we don't have time to go in convergent test. I did it for you. So the first thing I checked was the for the PB0 functional, how the total energy changes when we modify the expansion in plane wave for the R3 Fock energy. And you see that this is you don't need to go up to 160, that would be the default in Quantum Espresso, already 80, but actually if you look at the scale of this on the y-axis, you see that already 40 is a very good choice. You're doing an error that is very, very small on this scale. So this means that we can safely choose 40 Rydberg as the value for the Cutoff Fock. The convergence with respect to the Q point is more delicate, and here to show you why it's really important to use this Cauchy-Baldereschi scheme, I plot the convergence again of the total energy. If I don't include any correction for the divergency, this means that the point Q plus G equal to 0 is simply ignored, it's put to 0. So you are doing an integral and you are neglecting completely one point. That is an extremely important point because you have a singularity there, an integrable singularity there. So if you neglect it, you see that the total energy goes down very slowly when you increase the number of Q points, and you probably are not even converged at 12, 12, 12. If you then use the Cauchy-Baldereschi scheme, you have the blue points, and you see that now probably already at 6, 6, 6, you are very, very well converged, but even 4, 4, 4, it's a good choice. And if you include also the extra trick and you do an extrapolation very close to gamma, you have a much better convergence. And the same is true for the bandgap. So this is the direct bandgap at gamma. So if you don't put any correction, you converge very slowly. With this scheme, you are much fast in converging. Okay, sorry, this was for the direct gap at gamma. The same is true for the indirect gap at gamma. Okay, so now we can really go and see how this calculation looks like. So let me go back to the virtual machine. Okay, this was the band structure of our silicon that we discussed. So let me go one on the up folder. Okay, and now we go to exercise 1. This is where we have the input file. We open it again and we see that we want to do an SCF calculation. Again, here we specify the pseudopotential file, the prefix. This is the same structure we saw before, and here you have the relevant parameter for the hybrid function calculation. Here we want to do a PB0 calculation. We use, as we saw, a reduced Q point mesh that is 444. So we don't go for the 12 by 12 by 12, essentially thanks to this Cauchy-Baldereschi scheme, and we use the Cutoff equal to 40. And then again, everything is pretty much the same as we already see. Now the only difference is that this calculation is going to take more time than the previous one. Okay, so for some reason this is very okay, but this is you see now this is probably going to take a couple of minutes. So while this is running, let me just tell you a few things about how the self-consistency is achieved. Okay, this is just a recap of the parameter we decide to use. So what the code needs to do now is not simply a self-consistency on the total density, but also a self-consistency on the artifact potential. So the way it's implemented in Quantum Espresso is via a so-called nest loop, where essentially you have an outer loop where you do a standard SCF calculation. So you fix the artifact potential using some best guess for it, and you do a standard SCF calculation where this piece in the Hamiltonian is keep fixed. So you converge the density as we saw in the standard PB calculation. Once this is done, you go. Sorry, this is the inner loop. Apologies. So this is the inner loop. So you fix the artifact. You don't touch it during the self-consistent calculation, and you do the convergence on the total density as we saw for PB. Then at this stage, after this step is done, you would have a new set of connection wave function that you want to use to compute the artifact potential, and this is what you're gonna do. So you now update also the VXC and you iterate this loop. Eventually, at every iteration, you check whether your energy is converged or not. If it is converged, you are happy, your job is done, and you exit. Otherwise, you update VXC and you go and you iterate until the convergence is reached. And this is what you see exactly here. Let me go a bit up. Okay. So again, it's what is happening here. So you see, at a certain point, we see total energy, meaning that one of these inner loop is converged, so the density has been calculated. I have an estimate for the total energy. And then the code say, now go back to refine exchange calculation. So in this step, the code compute the new estimate for the artifact potential, update it, check that this estimation of the exchange energy is, in this case, still higher than the threshold, so it's going to do an extra step. So this needs to go to 0 if we want the calculation to be converged. So this is not the case. So the code is going to refine the exchange calculation, meaning it's going to update the artifact potential, and start again with an SCF loop. And you see now with oops, this is very slow. Okay, you see, start the first iteration, and actually at this stage only one SCF iteration is enough. So the code says the self-consistent, meaning the inner loop is already converged, prints out a report on the Kohn-Sham eigenvalue. Those are 72 keypoints, so quite a lot, but you see then it prints out again the new total energy in the presence of the updated artifact potential. Again, it checks the error on the exact exchange. This is lower than before, but still not enough, and it goes back and updates again the artifact potential. Once this is done, he can do again an inner loop calculation. Again, this took only one step to converge, because probably we are very close to the ground state. Again, a report on the eigenvalue. Okay. Other estimation of the total energy, other estimation of the exchange error. Now we are almost very close to probably to convergence. This is exactly goes on until you reach the convergence. You are at the end of the simulation, where essentially your estimation for the error on the exact exchange is smaller than the threshold we set in input. So the calculation is done, and you have your final final result. So now everything is written in this out file. So if we want to extract now information, well, either you again, open your input file and you search for instance, if you're interested in the Bandgap, you search for occurrency of these highest occupied, lowest unoccupied energy level. Here, just to facilitate, I prepare a script for you. So if you execute it, you get what is the total energy, what is the indirect bandgap, 1.84 electron volt, what is the direct bandgap, and the bandwidth is something the width of the valence band. Okay, and this is how to do a PB0 calculation. Now, as an extra example, I prepare also a simulation for HSC, which is a range-separated hybrid function. In this case, what I want to point out is that essentially, because this is a range-separated hybrid function, we actually zero artifact component on the long range. This means that we have no such a Q equals 0 divergence anymore, and this meaning that the convergence with respect to the Q point is much faster, as you can see in this plot. So even if you don't put in any correction for the Cauchy-Baldereschi, already 3 by 3 by 3 is enough to converge the simulation. If you plug in the Cauchy-Baldereschi correction, you are almost converge even with a Q mesh of 2 by 2 by 2. And again, the gap converges a bit slower, but you see that for 4 it's already enough, and there is no such a big difference anymore between the uncorrected scheme and the corrected one. And the same is true for the indirect bandgap. So in this case, again, we can set up the same parameter. So there is nothing very new in here, but this is exercise 2. This is again as before. We can see the input file, and now the only difference with respect to the previous one is that now we specify as the input density function theory we want to use HSC, and then again you can run it in this way, and you would see the same behavior as the one we discussed for PB0. So while this is running, let me go back to the slide and let me just comment the result. So now what we did, we computed the band structure of silicon. Well, we look at the band gap of silicon with the PB function, with the PB0, and now HSC is still running. And now I just show you a table with a summary on the result that we have. In particular, here you see the indirect band gap, so the smallest energy separating the valence to the conduction band, the direct band gap at gamma, which is also relevant in many experiments, and the bandwidth is the width of the valence band. And here in the last row of this table, I show experimental value, and you see, as I was mentioning before, PB is not doing very well for the band gap. The bandwidth is instead in much better agreement with experiment. PB0 overestimate actually both the indirect gap and the direct one. It also widen the bandwidth probably too much. HSC instead, thanks to its range separation essentially, and somehow mimicking the screening happening in a semiconductor or system with very small band gap, is actually much closer to experiment. In this case, the agreement is very good compared to experiment. So okay, this is the calculation on the virtual machine is still running, but you see we shouldn't be very far from the end of the simulation. Okay, while we wait, let me say maybe I have 5 minutes more. Let me say something about in general how hybrid functional performs. Here I just report some table from the literature to show you that this is the mean absolute error on a large set of 148 molecules. This is for the atomization energy, so the energy you need to break a molecule into its separate atom. This is a large set. G21 is a subset of it, and you see that LDA and PB has a kind of large error. These are kilocal per mole. Ideally, you want to reach less than 1 kilocal per mole. This is what chemists would call chemical accuracy. While you see that B3LEAP and PB0 greatly reduce the error, and we are almost very close to chemical accuracy. The same is true for solid. In this paper, they benchmark few hybrid functional PB0, actually PB0 HSC and B3LEAP, and look at the lattice constant of solid and the bulk modulus of solid. And also in this case, you see that the error is at least for PB0 and HSC is reduced compared to PB, and the same is true for bulk modulus. Okay, HSC is very famous for I mean, giving a better estimation of the bandgap. Here I just report a result from one of the developer of this hybrid functional scheme. You have an improved bandgap, and you see that the HSC result lies on this diagonal line, meaning that they are in very good agreement with experimental bandgap, and this is for a very large set of simple and binary semiconductor and insulator. So if you want to have a good prediction of the bandgap, maybe you need to go to hybrid functional. But let's just close with some caveats. So essentially, and this is what you probably already see, these are way more expensive than standard density functional theory, both time-wise and memory-wise. So there are no hybrid functional pseudopotential. So, and this is an inconsistency. I said at the beginning, you should always use the same pseudopotential, the same functional as the one that you use to generate your pseudopotential. There are no such pseudopotential for hybrid functional yet. So this means that this is a kind of inconsistency. So the good practice is to use always the closest one. So at least the one you use for the semi-local part of your hybrid function. For instance, if you use PB0, it's great to use, I mean, the best you can do is to use a PB pseudopotential. Non-local correction are not well defined, again, because now you are mixing between artifact with some local functional, so better to avoid pseudopotential with non-local correction, so always good to check whether your pseudo has it or not. Something that is probably needed and important is to include also semi-core state. So typically you need more, harder pseudopotential to converge better, to converge the quantity of interest. So typically this is something you need to check. So you need to include more and more semi-core state explicit in the valence and check that the results are not gonna change. And this you need to change the pseudopotential essentially. Everything is almost everything is implemented in quantum espresso, but also with not everything, but almost everything also with ultrasoft and PAW, but those are typically is lower than normal conserving pseudopotential, so it's a good advice to use non-conserving pseudopotential. Not all the features actually implemented for ultrasoft and PAW. And you may have realized that I didn't show any band structure for the hybrid function, essentially because it's not possible or easy to calculate essentially what is the eigenvalue at an arbitrary k point. You only have eigenvalue from an hybrid function on the very same grid that you specified in your SCF calculation. So this was a 12 by 12 by 12 grid. So you cannot do this in a simple way, but one way to get a band structure is through a relation that you're going to see later on in this tutorial. Okay, and I think that's all from my side. I hope I stay in the time. I think so. So I stop sharing, and I ask Iurii to continue this presentation.
Thanks, Nicola. Meantime, I saw there's a question in the chat that I marked as a question to discuss live. That is exactly this issue of how to compute bands with hybrids. I think that you have already almost discussed or almost replied to the problem.
Yeah. So if so, essentially, maybe I can go back to the expression for the hybrid function. Yeah, so essentially the only wave function and eigenvalue you have in a hybrid function calculation are the eigenvalue at the k point and the k plus q point. So, and this is always a mesh that is commensurate with your original mesh that you specify in the k points list. And this is so in principle, if you want to have an eigenvalue at an arbitrary k point, you would need a regular mesh of q point around that k point. But this is not. This is something that you don't have in the simulation. It's not easy to do a non-SCF calculation with this. You need to introduce a completely different grid. So I think there are different ways to address band structure, and probably the most effective one, at least in my experience, is through Wannier interpolation. So ideally, once you get your energies and your eigenvalues and the wave function on the regular grid of k point, you essentially do a Wannierization. So you write your Hamiltonian in a better, or in a very localized basis set, for which then you can do an interpolation in real space, and you can go back in reciprocal space at any k point you like. And I think this is something you are gonna see later on in the second exam of today.
Thanks a lot, Nicola. So if there are no other urgent questions, we can switch to Iurii and then have a longer Q&A session at the end. Iurii, please.
Thank you. Hello, everyone. Let me share my screen. Okay. Yeah. So thank you, Nicola, for this very nice hands-on on the hybrid functionals. So in the remaining 45 minutes, we will discuss about meta-GGA, and in particular scan and the family of scan functionals that became very popular in recent years. Okay, very brief theory reminder about meta-GGAs. So here in this red rectangle, I show the expression for the energy for some general meta-GGA functional. So n up is the spin up density and n down is the spin down density. It's defined as the integral of the total charge density, NOR, and epsilon exchange correlation is the energy density, which can depend on many quantities. So in particular, the up and down spin components of the density, the gradient of these quantities. There's some noise coming. Okay, sorry, we need to mute other speakers. Just a second, sorry. Okay, sorry. So coming back again. Yeah, so the energy density epsilon can depend on many quantities, like the up and down components of the spin charge density, the gradient of the up and down components, the Laplacian, and also the kinetic energy density, tau spin up and tau spin down. So this is the most general expression. There is a plethora of meta-GGA functionals. Here I show some of them, like BR89, TPSS, also popular one, scan, R-scan, R2-scan, etc., etc. So really many. And in this hands-on, we are gonna play a little bit with the family of scan functionals. Scan, R-scan, which stands for the regularized scan, and R2-scan. So in this scan functional, we actually don't have the Laplacian of the density. We just have the density and the gradient of the density, as well as tau, which is the kinetic energy density. So scan was introduced in 2015 by Perdue and co-workers. So scan stands for the meta-GGA functional that satisfies all known exact constraints, which are 17. But then actually it was realized quite quickly that scan functional is quite difficult to use in practice because of numerical issues, convergence issues. So then later on, there was introduced a new version of scan, which is called RScan, regularized scan. It solved the numerical convergence issues. It's more robust numerically, easier to use. However, this violated some known constraints, so we sort of lose a little bit in terms of accuracy. And then later on, again, people try to use the best of two worlds, so the accuracy of scan and at the same time numerical efficiency of RScan. So that was introduced, the R2 scan, which is the bridging really accuracy and efficiency. And this can be seen on the figure on the left, which is the mean absolute error as a function of the relative grid point count. So you see that you have scan here in blue, RScan on the top, and R2 scan at the bottom. So R2 scan is accurate at the same time efficient. Okay, now let us try to use scan in quantum espresso. To do that, we will take as an example the bandgap of silicon that also was considered by Nicola with hybrid functionals. So this is the input file that you already saw, maybe a little bit different with respect to previous exercises. But here I would like to highlight that we use experimental lattice parameter, but we can use a theoretical one as well. Again, in the next slides, I will discuss the cutoff energy, ECAT WFC. In this case, we fix it to 40 Rydberg, but we need to perform convergence tests to determine the optimal value for the cutoff parameter. Then we put this keyword input DFT equals to scan to tell to the code that we want to perform DFT using the scan functional. And to do so, we need to use the libxc, which is the external library of exchange correlation functionals. So Quantum Mobile was, in Quantum Mobile, we installed Quantum Espresso that was linked to the libxc. So let me quickly show you what is that. So if you write in Google libxc, you find this link, you press on it, you go to functionals, and here you have a list of many functionals like LDA exchange, LDA correlation, etc., and so on. It's really a long list. So we took that library and we compiled Quantum Espresso using that library. Then another point I would like to highlight is the pseudopotentials. So since we want to use scan functionals, ideally we need to have pseudopotentials that were generated using scan functional. Luckily for silicon, we have a pseudopotential generated using scan functional, and this is from this website. If you go there, you will see that there are pseudopotentials for a bunch of chemical elements, not the whole periodic table, but just light elements. So luckily we have for silicon one. And for the K-mesh, again, we need to perform convergence tests as before. Here we use just some initial guess, but we need to optimize it. Actually, I already performed the convergence test, so 12 is actually already the converged value, as you saw also in the previous calculations with hybrid functionals. So in this hands-on, we will not perform convergence tests with respect to the K-mesh, but we will see and discuss a little bit about the convergence with respect to the cutoff. So if we perform calculations for silicon at different cutoffs, we will see that the bandgap behaves in this way. You see it's non-monotonic and very noisy convergence. You see there is a lot of noise at low cutoff from 40 to 100, still a lot of changes, and only around after 100 Rydberg, there is some kind of stabilization. So if we draw this stripe, which is more or less the region of convergence, so we can say that with the cutoff of around 110 Rydberg, we are converged to a certain precision, which is the error bar of this yellow stripe. And the value of the bandgap is 0.939 EV. Okay, so let's perform one calculation using a low cutoff 40 Rydberg because we want to run it fast. If we do 110 Rydberg, it will take several minutes, but we want to have a fast calculation with 40 Rydberg just for demonstration purposes. So we go to Quantum Mobile and we go to exercise 3. Okay, so here we see the input file for silicon that we just saw in the presentation. We see we use scan functional, input DFT equals scan, and we use cutoff energy of 40 Rydberg, and we use scan functional, scan pseudopotential for silicon. We run calculation as usual with the PW program. We type pw.x, read the input, and write the output in the silicon.pw.out and submit calculation. On my computer, it will take around 20 seconds, which is quite fast. So you see the code performs iterative solution of the Concham equation with the scan functional. And at the end, we obtain the ground state. So we are almost converged. Yes. If I scroll a little bit up, we see the total energy here reported in Rydberg. And since we're talking here about bandgaps, so here what is reported is the highest occupied and lowest unoccupied energy levels. So if we take simply the difference between two numbers, we obtain the bandgap. Now we come back to the presentation. So now we perform calculation for 40 Rydberg. So it's this red point here. But you can do this homework, reproduce this figure. So run the same calculation, but with different cutoffs. You should obtain exactly the same plot. So, okay, so what we learn here is that the optimized cutoff is 110 Rydberg, which is a lot, which is a high cutoff. Next, I would like to discuss the point of the FFT grid. So here I show that the FFT grid for 110 Rydberg is it's computed automatically, and it is 60 by 60 by 60. So FFT grid is the grid to perform fast Fourier transforms from real space to reciprocal space, but also in real space we use FFT grid on which we evaluate some quantities, like in the case of scan functional. On this FFT grid, we evaluate the exchange correlation potential in real space using this grid. And also, I would like to take another case of 40 Rydberg and to show you that the FFT grid is 32 by 32 by 32, almost twice as scarce as in the case of 110 Rydbergs. So what we can do is to use 40 Rydberg cutoff, but we use the FFT grid, which is different from the default one. So we use 40 Rydberg cutoff and the grid corresponding to the converged cutoff, which is 60 by 60 by 60. To do that, in the input file, we specify the cutoff energy 40 Rydberg. And to specify the FFT grid, we use these keywords NR1, NR2, and NR3. So this is the size of the FFT grid. If we do so and we repeat the calculation, we can do so, by the way. So so the calculation will be more expensive. So we just need to add here the FFT grid in R1 60, in R2 60, and in R3 60. Okay, save, and we submit the calculation. It will take a bit more time than the previous one. So by doing so, actually what we will find is that the value of the bandgap has changed from roughly 0.923. It went up to around 0.938, let's say, or maybe 937. So quite a big change. And actually you can notice that now the new value, this yellow rhombi, is actually much closer to our converged value. So the difference is only 0.002 EV. So this tells you that actually we can use lower cutoffs for the wave functions, but we still need to use very dense FFT grids where the scan exchange correlation potential is evaluated. So this is just some trick to reduce a little bit the computational cost, at the same time to keep the accuracy of the prediction. So as I told you, we used the scan pseudopotential. We were lucky to find it. But we are not always lucky, and sometimes we can't find the scan pseudopotential for our system of interest. So what people do, they use pseudopotentials that were generated using simple local or semi-local exchange correlation functionals like PBE, for example. So I would like to highlight two norm-conserving pseudopotential libraries, the pseudo-dojo. So we put here the name of the pseudopotential from pseudo-dojo library, or we can use another norm-conserving pseudopotential, also based on PBE functional, from the SG15 library. So we take, as an example, two different types of pseudopotentials from two different libraries. So the question we are asking ourselves, what would be the value of the bandgap? Would it be as accurate as the one with the scan pseudopotential? Would it be better or would it be worse? And this is the result. You can run these calculations on your own when you have more time. But if we use the same cutoff, 110 Rydberg, and we use the same K-mesh, 12 by 12 by 12, so we can see that with the scan functional and scan pseudopotential, the value of the bandgap is 0.94 eV, and the experimental bandgap is 1.17 eV. So it's pretty close. I would say it's quite good. But if now we use the scan functional but PBE pseudopotentials, we obtain results which are worse. So with the pseudopotential from SG15 library, we get 0.83. And using the pseudopotential from the pseudo-dojo library, we get 0.64. So the second row is quite okay-ish. So it's just 0.1 eV worse than with the scan pseudopotential, but it's not too bad. But if we use another pseudopotential from the pseudo-dojo library, we are much worse than with the scan pseudopotential. It went from 0.94 to 0.64. It's really quite significant worsening of the result. So why is it so that two different PBE pseudopotentials perform so differently? Shouldn't they perform the same, more or less? So, and the answer is here. It's all about nonlinear core corrections. So the fact is that in the pseudopotential from the SG15 library, the nonlinear core correction is false. So that is not used. Instead, in the pseudopotential from the pseudo-dojo library, the nonlinear core correction is true. And the fact is that in Quantum Espresso, the scan functional is implemented, but there is no implementation of the nonlinear core correction for meta-GGAs. So if we use pseudopotential from the pseudo-dojo library, we are introducing some error, some inconsistency, because if we use pseudopotential with nonlinear core correction, it means also in the code it must be implemented for meta-GA, for scan, but it is not. So we're having some error. While if we use another pseudopotential without nonlinear core correction, we are not introducing any error, and the result is actually way better, 0.83 instead of 0.64. So the take-home message is that just pay attention to this. So when you run scan calculations and you choose some PBE pseudopotential, just pay attention whether it contains or not the nonlinear core correction. And actually, the same problem holds also for hybrid functionals like HSE06 or PBE0. Exactly the same problem, because nonlinear core correction is not implemented for hybrids. So if you use PBE pseudopotential with nonlinear core correction for hybrids, you're introducing some error, some inconsistency. So probably it's better to use pseudopotential without nonlinear correction, hoping that the result will be more accurate. So this is the take-home message, very important. And just to check that, one may wonder, but what if just pseudopotentials are different, one is better, another is worse? And to verify that this is not the source of this discrepancy, I performed standard PB calculations with these two different PB pseudopotentials, and I found that Bandgap is 0.56 and 0.57, so which is almost exactly the same, which means both pseudopotentials are good, but it's just when you use it with method GGA like scan, and you have or not the nonlinear correction, the results differ quite a lot. So that was about scan and silicon bandgap. But I also mentioned about, oh, sorry, before going there, I wanted also to discuss the convergence rate. So I showed you that when I use scan with scan pseudopotential, we need quite high cutoff of 110 Rydberg. But if actually we perform the semi-local calculation with PB pseudopotential and PB functional, the convergence is achieved way earlier, around 50 Rydberg. So you see, it really depends on the level of theory, level of your functional. With PB, we converge fast, as expected, around 50 Rydberg, while with scan, they are very difficult to use in practice and sometimes quite often difficult to converge. And we need very dense FFT grids, so that's why the cutoff is very high, 110 Rydberg. Then what about others functionals? So we said we have libxc, we have plenty of functionals. So how to use that? So just to give an example, so the functional is read from the pseudopotential. If you use PB pseudopotential, the code automatically reads information from pseudopotential and detects which functional it is. So here we say it's PB, but if you don't, actually you can overwrite that. So in the pseudopotential, it's written PB, but also if you say in the input file, input DFT equals something, so that has a higher hierarchy, so it's higher priority. So it will be overwritten. So input DFT is stronger than what is written in the pseudopotential. But just to give you another way how we can specify PB, how it is coded. So either you say PB, input DFT equal PB, or you can have this long name with different pieces of information. So what are those? The first two are actually LDA exchange and LDA correlation. Next two, which is third and fourth, are GGA exchange and GGA correlation. And the last two are meta GGA exchange and correlation. So in the case of scan, you can specify it in a different way. So you skip the first four, like LDA and GGA, and you just specify the last two, which is meta GGA exchange and correlation. So index I stands for internal, because in Quantum Espresso there are also internally coded functionals, and L stands for library. So it's it stands for libxc. So you need to know the ID of the functionals. So why do we have 263 here and 267? To determine these indices, you need to go to the website of libxc. So let's do so. So this is the website, and let me find the ID of the scan. See if I type ID in the search, I type ID equals, no, actually, let's say I type scan. So I found a GGA component of scan, 553. No, it's not what we're looking for. If we continue, okay, we need 263, 267. So let's see. So we continue the search. Okay, I found it finally. So here it is, scan exchange of Sun, Ruzinski, and Perdue. So this is exchange, and this the same way you can find correlation. And the ID is written here. ID equals 263. This is for the exchange. In the same way you do correlation for MetaGA scan. And there are many flavors of scan. You can browse here and use them if you want. Then for rscan, there is no short name in Quantum Express, so you can't say input DFT rscan, but you can specify it using the second option by finding ID for the exchange, MetaGA exchange and MetaGA correlation for rscan. And for R2 scan, there is a short name in Quantum Express, so you can write R2 scan, or you can alternatively indicate the IDs of the functionals. There is no really deep reason why there is no rscan short name. There were some just small, let's say, technical issues, but there is no deep reason. And maybe in the future releases, it will be also implemented. But here I would like also to compare the performance of three flavors of scan, scan, rscan, R2 scan. And we can see, here I used PB pseudopotential because even though we have scan pseudopotential, but we don't have rscan pseudopotential, and we don't have R2 scan pseudopotential. So I wanted to perform some consistency comparison. So that's why I just selected PB pseudopotential and just changed input DFT. And we see, actually, surprisingly to myself, I thought that R2 scan will be the most accurate, but what we found in practice that scan is the most accurate, while R scan and R2 scan is actually a bit worse. I don't know why, but that's what we find. So you can perform these tests later on because we have just 20 minutes left or so. So yes, you can play, just specify R2 scan in the input file and recompute, repeat the calculation, and you should obtain exactly the same value. But the take-home message is that scan functional is indeed very accurate. It's often better than LDA or GGA. It's quite, it goes to the same levels of accuracy as hybrid functionals, though it's computationally much cheaper. But there are still some numerical issues when using it in practice. So silicon is a simple case and it works very well. But if you take some more complicated material, it's not that easy to use scan, and often you have troubles of converging your calculations. So for silicon, we have pretty good bandgaps with scan, but let's now consider metallic system, which is bulk iron, and it's ferromagnetic metal. This is the input file. So we use here again experimental lattice parameter, but we can use also a theoretical one if you want. Here we specify some tentative guess of the cutoff, 50 Rydberg, but we need to perform convergence tests as usual. Here we specify input DFT scan. And here we don't have pseudopotential generated with scan. That's one of those unlucky cases where we don't know what to do. So actually what is left is simply use PBE pseudopotential. And here I take the pseudopotential from the SG15 library because I know that it does not contain nonlinear core corrections. So I expect it to be more accurate than the one from pseudodojo when used with scan. And bulk iron, it has a small cell, so the brilliant zone is quite large, so that's why we need a lot of key points. I checked before and found that 20 by 20 by 20 grid is already gives converged results. But you can perform convergence tests on your own. So now we are talking not about the bandgap because it's a metal, but let's consider the magnetic moment of iron. So let's see how does scan perform compared to PB. Is it better or is it worse? So this is the magnetic moment of iron as a function of the cutoff energy. Again, this is just to show you how the magnetic moment converges as a function of cutoff. So, and let's actually run this calculation. So we go to exercise 4. And we simply need to type pw.x, read the input file, and write the output to iron.pw.out. So if previous calculation for silicon took about 20 seconds on my computer, this calculation will take actually 4 to 5 minutes. It's more expensive. So while waiting for the results, we can continue the discussion. So we see here the convergence looks this way, and more or less around 50 Rydberg we are already converged. So it's better than the case of silicon. So 50 Rydberg is already, we are there, and the magnetic moment is 2.76 magnitude more. So we do this, we build the same table as before. We report magnetic moments computed using different pseudopotentials and functionals. So again, I still want to show you what is the result using pseudo-dojo PBE pseudopotential that contains nonlinear core correction. So you see that the magnetic moment changes from 276 to 267. And experimental bandgap has quite big error bar. It's in the range from 1.98 to 2.13. So we can see that both scan calculations with two types of pseudopotentials overestimate quite largely the experimental magnetic moment. So in this case, it seems like pseudo-dojo is a little bit better, but it's just coincidence. The fact is that the scan functional is known to overestimate magnetic moment for itinerant magnets like bulk iron, bulk nickel, etc. So it's really a drawback of the functional, not of the pseudopotential. So scan for itinerant magnets is actually worse than standard PBE, because below you can see two PBE calculations with two different pseudopotentials, and both give 2.28, 2.26, still slightly overestimating the experiments, but PBE is closer to experiments than scan. And again, out of curiosity, we can check the performance of R-scan and R2-scan. We see the values changed a little bit, not much of the change, but all of this family of method GAs overestimate the magnetic moments of itinerant magnets. There are very nice papers by Tran and co-workers. They study other classes of materials like transition metal oxides and other families of materials just to see the performance of scan. So I invite you to check that paper. There is no general trend. In some cases, scan is better than PB. In some cases, worse. So it really depends on which material you study. So I really invite you to check that. But the take-home message when you deal with magnetic materials, you need to be careful when you want to use scan. Okay, that is for the next hands-on. We are done for now. The calculation for iron is still running. And probably we can use the remaining time to answer a couple of questions. We have still 15 minutes. Probably we can use this 15 minutes for the discussion about the whole hands-on, including hybrid functionals and LDA and GGA.
So Iurii, if just looking at Slack, there is just one question popping up that we may want to discuss live. That is, again, this effect of nonlinear core correction, or what is the issue with the nonlinear core correction in scan and so on.
Okay, I tried to be clear, but probably I was not. So let me try to repeat again, try to be more clear. So the fact is that in the implementation of scan and quantum espresso, there are missing terms. So actually, for the nonlinear correction, it's not implemented for scan. Okay, so this means that in principle, you should not use scan with pseudopotentials that contain nonlinear core correction. So in principle, you should not. But in practice, you can still do it keeping in mind that you are having some error. And we can see here in the case of silicon that if you use pseudopotential with nonlinear core correction, the result is not terrible, but it's worse than when using pseudopotential without nonlinear core correction. The same for the hybrid functionals, I would like to repeat. If you use hybrid functionals with PBE pseudopotentials, just pay attention whether those pseudopotentials contain nonlinear core correction. I would try to avoid using pseudopotentials with nonlinear core corrections. But if you don't have other choice, other pseudopotentials, probably you can still try to use it, but it has some error, hidden error.
Thanks, Iurii. If I may also further comment on, basically the nonlinear core correction is a correction that you add on top of the density. If your functional just doesn't depend explicitly on the density alone, and that's the case of hybrids and meta-GGAs, for instance, then you basically don't know what to do in nonlinear core correction, so you may run into troubles.
Exactly. Thank you. Okay, I see also a question from Slack. How can one find out if a pseudopotential uses nonlinear core correction or not? Yeah, you just need to open a pseudopotential. So let me, okay, it's finished, very nice. So in the hands-on material, if you go to the folder files and you go to pseudo, so now we need to open a pseudopotential and see if it has nonlinear core correction or not. So for silicon, I used silicon.pbe underscore pseudo dojo. So I open it. If you scroll a little bit down, there is a lot of information, how it was generated. And here you see core correction equals T. T means true. So this means you have this pseudopotential contains nonlinear core correction. It's from the pseudo dojo. So that's why I would not use it. If we instead we open another pseudopotential from the SG15 library, so it's silicon underscore on cv pb etc. So again, if we scroll down, here it is, and we look for core correction equals F, false. So here we don't have nonlinear core correction, and I would use it with scan. So that's how you can check it. Also, people ask the difference between scan, rscan, r2scan. Let me go back. You can take the original papers and check the difference. I'm not really expert in all these functionals. It's very technical, but what I remember well is the following: that scan is the first which one was introduced, 2015, and scan satisfies all known exact constraints that functional should satisfy. There are 17. So scan is accurate but numerically inefficient. rscan is the modified version of scan, where they improved the efficiency, numerical efficiency, but at the cost of the accuracy. Let's say they violate some constraints at the price of having more numerical performance. So rscan less accurate, but more efficient numerically. And r2scan is between two worlds. It's accurate and at the same time numerically efficient. This is what is claimed. I never used r2scan in my research, so I can't really confirm, but I think that's what is the status.
Then there's a question about the computational efficiency. You have already somehow shown something, but just scan or the other variants compared to PBE. Do you have a rule of thumb or a quick comment on it?
Sorry, I didn't understand. Could you please repeat?
Yeah, so what is the difference in computational efficiency? So how slower a scan, r2scan, rscan calculation is, besides these three are already quite different among themselves.
Yes. I might be wrong, but as far as I understand, it's more or less the same. I mean, for silicon, I haven't noticed big differences. So more or less, I would say, roughly speaking, the same order of magnitude. I don't see big differences. But I don't have a extensive background with this family of functionals, so I can't say in general, but at least for silicon and iron, I haven't noticed big differences in terms of timing.
Okay, thanks, Iurii. Then there's another question that is, are there any limitations of scan functions in the case of more complex systems like slabs, surfaces, for example?
I'm not aware. I'm not aware of those.
Yeah, so do I.
Yes, if someone knows, maybe you can comment, but I'm not aware of this. As far as I know, you can try to apply to any system.
Yeah, neither I'm aware of any specific accuracy in any specific quantities related to these systems, I have to say.
Yeah, I think they were designed to be general for any system. So that's why it's like hybrid functional. You can apply it to different materials, molecules, solids. So maybe you can try to fine-tune them, but as far as I know, scan is quite generic, functional, and apply to different materials.
I see another question about the issue of pseudopotentials and nonlinear correction. It says, reads, does this mean that while using pseudopotentials for our system, it is wise to test all different libraries? Does this also mean that some systems may not give useful results on using pseudopotentials that use nonlinear correction?
Okay, so one important message is that scan is not implemented for ultrasoft and projector augmented wave. So this means you already, I mean, this is what concerns quantum espresso. I don't know about other codes, but the quantum espresso is only norm conserving pseudopotential. So immediately you cut off a lot of libraries. So what is left is essentially Pseudo Dojo and SG15, which are both norm conserving. You can generate on your own another norm-conserving pseudopotential and try to use it, but I'm not aware of other norm-conserving libraries. Okay, maybe there is PS library, but it's not really tested. So I would be hesitant to run calculations without testing. So the bottom line is that there are not that many norm-conserving libraries. The ones which are famous, I show here, Pseudo Dojo, SG15. That's it. So, and we know that Pseudo Dojo contains nonlinear correction. So, however, yeah, very important remark that on the GitHub of Pseudo Dojo, there is actually pseudopotentials regenerated without nonlinear correction. Actually, Samuel Ponce from Belgium, he regenerated them. So you can try to use them if you want. So you go to the GitHub official repo of Pseudo Dojo and try Pseudo Dojo without nonlinear correction. Otherwise, SG15.
And then there's a question about the information about atomic wave functions included in the pseudopotentials.
Yes, Pseudo Dojo contains atomic orbitals or pseudo-atomic orbitals of wave functions, while SG15 is not, but then someone regenerated pseudopotentials including atomic orbitals. I don't really remember where is it, somewhere on the net. You can find SG15 including atomic orbitals.
Yeah, also as a side comment, I think that I've done also myself several times. Basically, there's an input file is reported within the SG15 file, and if you go to version 3 of the Don-Hammond code, you can really regenerate it on yourself. Of course, then you have to carefully check.
Yes, yes.
And of course, I mean, people have already done it. So if you find something from a table, that is even better.
Exactly. Thank you.
Then there's a general meta question. How does one as a researcher know a priori which functional and pseudopotential to use? Let's say I want to calculate something for which I don't have experimental results. When I can be confident that my results are realistic?
Yeah, it's a very good question. And actually, for that purpose, we created, well, our colleagues created AIDA Lab. It's like for experimentalists who are not experts in the computational physics. So, I mean, as we know, it's quite difficult to know all this, how to parameterize the calculation, choose functional, choose the potentials. So many details, one can easily get lost. And especially for beginner, it's not easy. So yes, I mean, either you become an expert. If it was as simple as just pressing the button and use it as a black box, it would be amazing. So nothing to worry about. But that in practice, it's not how it works. Depends on the property you want to compute. You need to choose level of theory you need, etc., etc. So AIDA Lab is for experimentalists, try to perform some basic calculations of some basic properties. It was designed to be like a black box, turnkey solution. Just press the button, you get the number. But we are all here because we learn that it's not as simple as that. So essentially, you need to become expert. Follow this kind of tutorials, learn, practice.
And so if I can, I mean, for pseudopotential, I mean, if those are correctly generated, this is easy to verify, because the pseudopotential, you just need to reproduce calculation from all electron. So in principle, you have a way to check whether your pseudopotential is accurate or not. But to know which functional is accurate for the property you want to describe, no, this is, as Iurii was saying, is something that you need some experience. So there are most situations where standard functional are already very good, but you need to know the limitation essentially. So yeah.
Can I add a comment?
Yes, please.
Just on the pseudopotentials, as Nicola said, you can always check against all electron, but there are cases sometimes where your all electron calculations look good for the comparison, but actually they don't bind correctly. So not to say it's even more complicated, but sometimes it's worth, for your given system, making sure that the bond lengths you have also make some sense. So there are more checks you can do, but often checking against structural parameters can help you verify whether what you're doing is realistic. Of course, this is not knowledge you can have a priori before you do the calculation.
Thanks.
Yeah. Sorry, if I just saw one question, which is quite important, maybe I made some wrong statement about pseudo-dojo, that one of the participants has noticed that in pseudo-dojo, it's written has wave function false, which seems like there are no atomic orbitals written in pseudo-dojo. While I thought they are written. Anyone knows anything about it?
I don't know. I suspect it may be due also to the time of generation. I think that the Naman code version 2 doesn't have the capability to include atomic wave functions. Version 3 has the capability. So I don't know if it's just a matter of that, or if some pseudopotentials do have atomic wave functions, others don't. I don't know.
Yeah, no, I thought it all included, but yeah, this is a bit strange. Yeah, apologies. Yeah, basically one has to check carefully if it's included or not. I thought it is, but maybe I was wrong. It seems I was wrong. Just one has to check it. We need it for DFT plus U, by the way. So if you want to use pseudo-dojo, you need atomic orbitals. So if you don't have it, it will not work. So yeah, one has to check.
So it seems there are no other urgent questions. I don't know, Iurii, Nicola, or if you see other questions you would like to discuss live. Otherwise, we are somehow very good on time, ready for a coffee break, 15 minutes, and then we
maybe just one last, if I can.
Yes, please.
Yeah, there is one. What about using RVV10 in QE? Is it available with scan? So I think yes. I never tried myself, but I think it should be compatible to use scan and RVV10. Oh, wait a second. So if you say input DFT equals scan, you can't say input DFT equals RVV10. So probably it is not compatible. But I know that there is a PRX paper by Sun where scan was, there is scan plus RVV10, where scan was, let's say, optimized to use together with RVV10. I'm not sure this is implemented in Quantum Express. So maybe Fabrizio knows, not sure.
Hi, Iurii, sorry, I was answering on Slack.
Oh, okay. But what,
Yeah.
do you know if it's implemented in QE?
Can you repeat the name of the functional?
Scan plus RVV10.
Yeah, no, so there is, I was wondering on that exactly, and there is RVV10, but not in combination with scan. I guess just with a GGA like a PBE or something.
Yes.
For sure, not with scan.
Yeah.
I'm not sure if you can try it and get something which makes sense, but it's something that we never did. So
okay,
I cannot give any guarantees.
Okay, but my guess is it's not available because to specify RVV10, you need to say input DFT equals RVV10. But at the same time, you need to say input DFT scan. So probably
that's true. That's true. You could, with just a small intervention of the code on the code, create a combination. But
yeah,
I cannot say anything more.
Okay. Yeah. Thank you.
So for the sake of the workshop schedule, perhaps we can stop the live questions here. Thanks again to Nicola Colonna Iurii Timrov for the very nice tutorial, and to all the tutors for answering questions on Slack and Live. So we reconvene in 15 minutes, or let's say we reconvene in 3:30, but on the other Zoom link, on the lecture Zoom link. Okay.
Thank you all. Thank you, Andrea.